Okay, so we resume our morning session. It is a pleasure to introduce Rodolfo Russo from Queen Mary University of London, who is going to talk about the dynamics of black hole binaries from scattering amplitudes. So please, Rodolfo.
Hi, can you hear me? That's fine. Okay, great. Let's see whether, yeah, maybe I prefer to do it the old way, which is the one that I know. Okay, very good. Okay, so let me first thank the organizer for inviting me and for putting together this wonderful workshop. It's always a great, it's also great to come back to Florence. And also because they chose such an interesting topic, which attracted people from many different communities to study the same physical problem. And what I would like to do in my talk is to bring the perspective of yet another community on the problem of gravitational binaries. And the title gives the idea, because I'm talking about scattering amplitudes, so something very tied to particle physics. And I would like to convey the idea that the technologies, the ideas that have been developed for study the particle physics system can be very efficiently applied also to study a part of the gravitational binary problem. So let me start with these slides that you already seen twice in Alba's talks and Gregorio's talk. So that's stolen from the original paper of the LIGO-Virgo collaboration. And it's a great cartoon because it immediately conveys the idea of the system we are interested in. You see the cartoon with the two celestial bodies that are spiraling around each other. And what happens is that the distance, the relative distance between the two bodies decreases as the in-spiral goes on. And you see in this little graph is writing this black curve going down is the separation in units of the Schwarzschild radius. So that's going down. And the velocity of this object is the green curve, and that's in unit of c, and it's going up. Of course, for a bound system, there is a relation between potential energy and kinetic energy, right? I mean, this, the total energy should be smaller than 0. So when the distance goes down, the velocity goes up. And then you see that the signal increases both in amplitude and in frequency, because when the two objects come together, they start spinning faster, and so also the wave detected, which is that signal, increases frequency. And this is the first part of the story, which goes under the name of in-spiral, as was already discussed, and that's the part I'm focusing on, right? So it's a bit of a complementary view of the first day, which was focused on the ring down and the quasi-normal modes, which is the final part. Now, when the separation is of order 1 in Schwarzschild unit, okay, that's X und Leones, right? That's where the complicated part is the merger, and that's the most violent part, but it lasts only very little, and then it transitioned to the ring down part. So keep in mind this scale, the black curve, the inverse of that scale, so R over B, that's the perturbative parameter I will be exploiting to discuss this in-spiral phase. Now, I got interested in this problem a few years ago in 2018, here in Florence, so I'm very happy to give this talk. And the motivation was a talk that Thibaut Damour gave at a workshop that we organized around the same period of 2018 to celebrate the 50th anniversary of the Veneziano model. And Damour presented this paper, and you see that in the title, the word scattering. So that's when, okay, I got the input from people from the GR community that particle physics and scattering problem could be relevant for the bound problem. right, for this problem. I mean, in principle, they look like completely different things, but from the title, and in particular, look at the final sentence, right, of the abstract, says, we indicate a way to connect our classical result to the quantum gravitational scattering of two particles, and we urge the amplitude expert to use their technique to compute two-lap scattering amplitude of scalar masses. Right, so I will focus on that and try to give the idea why this level of precision, this two-loop, will be certain precision in the perturbative parameter we're discussing, this R over B, why that is the kind of the first interesting place for this in-spiral problem. Okay, so the general approach is very naive, and the idea is to model celestial bodies as just elementary particles. And with my string theory hat, as Joseph was saying, on, I would say that this is particularly appropriate for black holes, right? Because even if in this cartoon black holes are depicted as gray balls with the Schwarzschild radius, right? The orthodox GR point of view is that, as Joseph was saying, is that there is nothing at the horizon, right? So from the GR point of view, they should really be object basically focused on the high curvature region, right? So this input, which seems crazy, model celestial body with elementary particle, actually looks what theory predicts for black holes. And the input, what I need, is to give the couplings between these elementary bodies and gravity, right? Or in general, for more general theories, to all soft particles, right? So that will be the input. And you can look at this input in two different ways, either in an effective field theory approach, where you just say, okay, that's my effective couplings, and then I can write corrections with higher derivatives, or in a UV complete theory where you give a microscopic definition of those objects, I don't know, in terms of D-branes or strings, and then you should be able to derive those couplings from your fundamental theory. Right, so in either way, at the end, the input for the program of using amplitudes to describe the in-spiral phase is just the set of couplings of your point-like but very massive object, which represent the black hole, the celestial bodies, those couplings with gravity. Then there is the technical part, part number 2, is to use the amplitude technology to describe the large distance scattering, that's following the Moore's idea, right? And then extract the classical limit, right? So if when you calculate the full scattering, you have more than classical GR, right? You have all the quantum effects. And what I want like to do is to give you an idea how we separate the classical results that are relevant at large distances from the quantum corrections that are naturally included in the scattering amplitude. And then the final bit, which I will tell very little about today, it's not my field of expertise, is to bridge these two problems, the scattering problem and the bound problem, and extract information from the scattering problem that is relevant to the bound problem. And basically the idea is that you can extract information on the effective gravitational interaction between these two bodies and use it in the effective one-body approach or other approaches to create templates for the in-spiral part of the gravitational waves. So what I would like to just stress is that from the conceptual point of view, what is appealing for me is that it's a very general approach that is not just tied to GR or one theory. Once you have a perturbative theory of gravity, you can run through this approach, right? And actually my particular kind of approach was from formal to practical. So we started looking at this problem in string theory, where instead of having black holes was scattering of strings and D-branes, and then went through supergravity and then to GR, right? And you will see that things get technically complicated when you get to GR. So it's usually good to have toy models like supergravity, where you can understand the physics and then look at GR as a second step. But also, it's very flexible because you can change what are the celestial bodies you are interested in. They need not to be just a model object that models Schwarzschild. They can model Kerr. They can model shock waves. If you have a complicated theory, like it can be bound state of strings and d-branes. You still, if you have a perturbative theory of gravity, you can run this approach. And the general flavor that you get from this calculation is to see how classical physics arises through exponentiation. Right, so through the idea that the interaction is mediated by many exchanges of soft particles, that the radiation itself is a kind of a emission of many soft gravitons, right? The object that we measure, right, the waveform is itself made by many soft gravitons. So exponentiation will be kind of the thread, the technical thread in this approach. Of course, you can say, okay, that's very nice. It's maybe interesting, but is it useful, right? What can you add, right, as a new community to this area? Well, I mean, it's true that any new perspective usually brings something interesting, but let me just take a partial and personal list of new results and developments that have been that emerged in the last 3-4 years. That's when this kind of area became very active. So that's there is much more. That's just my take. So one of the first type of results that attract attention is explicit results in the PM expansion. PM stands for post-Minkowskian. And that's just a buzzword for the expansion that I was mentioning before at the very beginning, right? So it's an expansion in the ratio between the Schwarzschild radius, or the size of your object, and the relative distance, B, right? So in the Schwarzschild radius, there is a factor of the Newton constant, a factor of G. So that's the loop expansion in the standard amplitude approach, right? So that's what PM expansion is. And 3 PM corresponds to 2 loop, right? So this challenge, in some sense, was first taken on by this collaboration based mainly in California, Zwibern, Parra-Martinez, many people. These are really impressive papers, and I think they really kind of gave a concrete proof of principle that, okay, this is something that is concrete, right? Is useful and can give results. On the conceptual side, I like also this idea that the group of Porto, Kalin, and collaborators had to find a real direct link between the scattering problem and the bound problem. So at least for a certain type of observables, what they show is that you can do a very naive and explicit analytic continuation of the results that you get for the scattering problem. Basically, take the energy and make the energy negative. Right? So energy positive is scattering, energy negative is bound state. And you have also to do an analytic continuation on the impact parameter to keep the angular momentum real. And you get on-the-nose results in, for the bound problem. Right? So there are just also conceptual development that can show this deep link between these two problems. Also, this group, again, based in California, has very nice results on other type of observables that are really kind of related to radiation, like the radiated energy, the angular momentum. And these are results that, on observables that people in the GR community, of course, knew in part, in an approximation that is called post-Newtonian, so where you expand also in velocities. But these results, these more recent results, resum a whole series of corrections and give compact, nice relativistic expressions that I don't think were known before. So it again shows that this approach has the potential to give new new result. Something which is, I mean, you see all these papers are very recent. I tried to cite the latest one, but there is a lot of activity, so you can go to the references and look back. There is a lot of activity in modeling and even understanding what does it mean to model a Kerr black hole, so a spinning object with a classical spin. And I think this is very, very interesting. And then let me come to what I will be mainly focusing on, is to look at a regime that exists only in the scattering process. So you may say, okay, maybe that's less interesting, but I will argue that it's still interesting anyway. And this regime is a regime where you take high velocities, right? So when you are in a scattering process, the kinetic energy is not related to the potential energy. You can keep the distance large, but crank up the velocities as much as you wish. And then you can ask, is it consistent to model the scattering object as point-like object or not, right? Or maybe it's not consistent. Maybe you see there is a new scale even at very large distances, right? So in some sense, there is a conceptual aspect. And the other sense, you will see that it's also very practical problem because this high energy regime highlights different type of contributions that you will see, potential, radiation reaction, that they were already known to exist in the PN approach, but I think this highlights very well the role they play, right? So this is a set of papers that I've been working with Paolo Di Vecchia, Carlo Heisenberg, and Gabriele Veneziano, and so that's been really great fun.
Sorry,
yeah,
question.
Please.
Are there attempts to try to include in this framework finite size effects?
Yes,
modeling neutron stars?
Yes, definitely. Actually, that's the talk I wanted to give in some sense, given the, and I will come to just mention, but I could not give because I don't have a result on that. But I think that's very interesting thing, and actually I also wanted to ask you. In some sense, this finite size effect should show up at a certain level of precision, correct me if I'm wrong, also in this in-spiral part, right? And
5PN, it's a 5PN correct?
Yeah, exactly, right? So the idea is when the precision is good enough, then, oops, okay. Was the cell. It might be also that part linked to some fundamental physics of this elementary object, right? So I think that's for me is one of the motivation, right? Yeah. Good. Okay, please do interrupt me any time, right? If you have questions. Yeah, please.
So this analytic continuation, is it valid for any kind of orbit, like when you have precession and eccentric stuff? So in principle, I'm not saying that people have already computed it, but it's in principle valid for genetic or restricted to simple cases?
Yeah, actually, I think in principle, yes. I mean, I can tell you a bit more toward the end, but this analytic continuation in some sense works better for the orbits you don't want. So for the very eccentric orbit. So maybe in future, right, for if the masses are very different, these orbits will be also relevant. But now I understand that are all almost the circular orbits. But in principle, yes, you can do, and also when you start including spin, the motion is not on a plane anymore, right? So, yeah, I think there are a few papers by Porter, I think it's the latest one, the one I cite probably also has spin. So yeah. So where this idea of the analytic continuation does not work as well is non-integrated quantity. I mean, if you really wanted to map the waveform, not the total energy emitted or the scattering angle, the period, right? But if you wanted to map the waveform, then I think that's still open problem. Okay. Okay, so this is kind of the motivation part, but basically it's all the content of the talk is here, and then it's just technical, so you can you can sleep. But let me just give you some also formula just to say that this is not just wishful thinking. So this is a cartoon of the process we are interested in. So here there is a space-time picture. Let me do the simplest case. So the model Schwarzschild black hole, so just a massive object. So you have two objects, one of mass m1, one of mass m2. They come with some velocity. B is the impact parameter, right? And so basically the distance between the two objects, and they deflect. So one of the main observable is this guy, is this deflection angle. So if you do the analytic continuation of that deflection angle, you get information about the period and basically also the, things like that. So on the right-hand side, you have a diagrammatic picture of this process. And you see I tried to separate the two ingredients. So the blue and the red line are the massive classical objects. And I take as an input the couplings between this object and n gravitons, right? These are the soft particles. So this square region, that's the input, that's what I know. And then what I should do is to calculate always the diagrams, all possible diagrams that connect the up part and the low part without forming loops inside, right? Because I just want classical physics, so I don't want graviton loops. Right, so the first way is just to connect them with straight line, just with propagators. That's the first diagram, but then you can have non-linearities of gravities, vertices, right? So just connect in all possible ways. So that's what we want to calculate. And the key quantities are the center of mass energy. This sigma, I should probably have to call it gamma, is basically related to the relative velocity, is the gamma of one particle in the frame of the other. Right, 1 divided the root of 1 minus v squared. J is the angular momentum, the orbital angular momentum of the process. And the difference between the incoming and the outgoing, right? So, okay, for me it's P1 plus P4 because I'm using momenta all in the same direction, right? That's the transferred momentum, right? So this Q is related to this deflection angle, right? So what I'm stressing here, I write this Q as big Q, because this Q is big, right? So you have a classical object, you have a black hole which changes direction. So there is a classical large exchange momentum, right? So this is, even if the angle is small, chi is small, Q is huge. Very good. So this is the picture. And then you say, okay, then it's very hard. I will not be able to do any calculation because I should calculate an infinite number of diagram. I give myself problems, giving the microphone to him.
Okay, but probably you are going to say, but usually in this kind of game, if you consider the icon, your sum, everything, there is one diagram which is the most important with a fixed number of
Very good, very good. Yes, yes. So he's spoiling my point, right? You see. So yes. So I stated the problem, but there is a solution, right, of this problem of calculating an infinite amount of diagrams. And so let's see exactly, try to unpack what Igor was saying. Let's see how this solution comes up. Start calculating the first diagram, right, where we exchange only one soft particle, one graviton, right? Okay, I have a minimally coupled scalar with mass m2, a minimally coupled scalar with mass m1. I can do a 3-level Feynman diagram. That's the result here, which I write for two theories, just to give you an idea that you have an option. On the top, you have n equal 8 supergravity. On the bottom, you have pure GR. And that's the result. And let me just stress that you see the result is different, because in n equal 8 supergravity, there is also the exchange of the dilaton. The dilaton couples to the mass, right? So there is another soft particle, so the force is different, right? But if you take sigma to infinity, so you do the large energy behavior, you see the two results get the same. So this is another theme I will try to stress. There is a universality of the high energy regime, because you expect that in the high energy regime, graviton dominates, right? And so, yeah. Then you say, okay, but this is not what we want to calculate because a single graviton carries very little momentum, and the momentum carried by that graviton is basically h bar over b, right? So let me try to change this answer in an answer written in terms of classical quantities. So instead of small q, let me introduce b, the impact parameters. So you do this via a Fourier transform. It's easy, we can calculate. And then if I write the d equal 4 result, and I restore the factors of h bar, you see that that answer on the top becomes this answer here, and you see that it goes like 1 over h bar. And then it seems strange, right? It seems that this answer does not have a classical limit. I send h bar to 0, and then this three-level diagram blows up. Right? So what is the cure? What is actually telling us this result? It's telling us that we should include, that the naive perturbation theory is not the right approach, right? Just considering one graviton and saying that the exchange of two gravitons is subleading with respect to the exchange of one graviton is not correct if these objects are classical, right? The masses are large, right? So let me calculate the two exchange, right? And then follow the same idea here, saying that the exchange, the momenta of the individual gravitons are small because of order h bar over b. And so I'm interested in the leading non-analytic behavior for small momenta of the individual graviton. When I do the Fourier transform, this translates into a large distance effect, right? So I'm calculating the amplitude. This A1 is the one loop amplitude. And then after you do your Feynman diagram, your integrals, you'll see that the leading contribution for small q goes like q square to the 1 plus epsilon in d equal 4 minus 2 epsilon. And this coefficient A1, which is a function of the velocity, right? So it's not a number, it's a whole function, actually is exactly the square of what we found at tree level. So it's the square of this A0, sigma square minus 1 over d minus 2. And it has the signs and the i's, right, to say that it starts exponentiating this tree level, right? So if you take the leading contribution as q becomes small for the exchange of one graviton, two gravitons, 3, 4, 5, etc., you resum, right? All these leading 1 over h bar terms resum into an exponent. So if you take this exponent, you do the expansion, right? This A0 goes like 1 over h bar, right? So if you do the expansion, you will have a term which is 1 over h bar, which is the tree level, a term which is 1 over h bar square, which gives this leading contribution at one loop, a term which is 1 over h bar cube, which will be the leading contribution of three exchanges, so on and so forth, right? So the fact that the 1 over h bar goes at the exponent is exactly what you expect for classical physics, right? Because at that point, the object at the exponent is the classical action. The classical action becomes large when h bar becomes small, but that's what you want. But it's just a phase, right? So it's not a problem, right? Now you say, well, but look, there is a subleading term, this A2. And if this leading term goes like 1 over h bar square, the subleading term goes like 1 over h bar. So at one loop, you have a new bit of information, something that you cannot, it's a new bit of classical information, something that you cannot derive from the tree-level diagram. It has the same feature of the leading term of the tree-level diagram, so it will also exponentiate. So what happens is that the existence of a semi-classical limit requires that the 2 to 2 amplitude takes this form here in the box, where the only term which diverges as h bar goes to 0 is in this exponent. And it is 1 over h bar, right? You don't want to have 1 over h bar square the exponent, right? So in the exponent here, you have 1 over h bar. But this object that I call it delta because the icon, right? Usually is the symbol that people use. This object here, delta, itself has an expansion something that you derive from tree level. That's the most important diagram that Igor was mentioning. Something that you derived from the one loop, this A21, and that's a first correction to this iconal. So I called delta 0 the tree level, delta 1 the one that comes from one loop. The one that comes from one loop has more factors of G, right? Because here at tree level you had a factor of G. Here at one loop you had a factor of G squared. So this expansion here at the exponent is not an expansion in H bar. It has 1 over H bar overall, but is an expansion in G, which means it's a PM expansion. Okay, so basically this is, the whole idea is here. Right? So I don't know if there are any questions on this.
So you are in the, you are thinking of iconal expansion that is large S, the ratio of S over T and so on, because I was thinking you are considering the small angle scattering.
Small angle, yes. That's the only thing, right?
Okay.
Yeah.
So you are
yeah, this PM expansion
in the called the
Regge
Regge limit. Just a curiosity, probably, I don't know. If you consider the gross Mendel limit S over T constant, it should be corresponding to a large angle scattering. Could this have anything to be to the inspiring where you have?
Okay, yeah, maybe let's postpone. So yes, what he's referring to is to go away from this approximation where the objects are well separated, but do a head-on collision. So a head-on collision is what Gross and Mendel tried, and that's much more difficult. So yeah, I don't have much to say on that. So okay, so let me just say, okay, what do you do with this delta? Right, so if you wanted to go, let me use this deflection angle as the prototypical observable that you want to extract. Well, okay, once you have extracted that delta from loop diagram, what you can do a Fourier transform back in momentum space. So you have to do this Fourier transform. And this Fourier transform is, of course, very difficult because this delta is a complicated function. But since delta goes like 1 over H bar and becomes large, you can do it through a saddle point approximation. Right? So when you do a saddle point approximation, you easily see that this is the result of the saddle point. So it gives you a classical value for the large Q. Right? So this is the large Q we advertised at the beginning. Right? And you see arising from delta. And once you have large Q, okay, this is related to the deflection angle, so you get the deflection angle. So here I write the result of the iconal, here from the n equal 8 supergravity, and from the deflection angle, which is just derived from the iconal through this relation, for GR at 1 p.m., at 2 p.m. Now, as Damour was saying, this is not the interesting part, right? So, okay, we played a lot with this, we had a lot of fun, but he was saying, okay, 3 p.m. two loop is the most interesting part. And the reason for that is that these numbers here, these functions actually, these results, you can derive them from a probe calculation. They're entirely determined by geodesics in the Schwarzschild metric. And the same for n equal 8 supergravity, right? It's a probe calculation not in the Schwarzschild, but in the solution relevant for this Kaluza-Klein state that we use for modeling the massive states in n equal 8 supergravity. So in some sense, this is no new information besides the solution of Schwarzschild, right? So I could write the solution, look at geodesics, calculated the deflection angle from geodesics. Let me skip this slide. And then you see in that paper, maybe it was known before, but I learned from there, end of 2019, Damour gave a very nice formula to link the probe calculation with this dynamical calculation, where probe calculation means you take one mass much larger than the other, right? You send M1 much larger than M2, but you can reconstruct the result with M1, M2 general for 1 p.m. and 2 p.m. from this probe calculation. Now, this is not true at the next order. So this is something I want to stress. So this in-spiral problem, when you have two dynamical objects, go beyond the information that you get from the geometry. Right? So you have Schwarzschild, right? And you can say, for me, Schwarzschild is the solution, or Kerr is the solution. But that solution does not have all the information you need to construct the waveform of the system, right? Just because gravity is non-linear, right? So if you have one solution, you have another Schwarzschild, you cannot sum them and say that's the new solution, right? So you start seeing this very explicitly at 3 p.m. 3 p.m. there is new information. Yeah.
Very naive question, maybe. So why is it that you can get 2 orders in G from the probe? I mean, I would think maybe you just get the leading order.
Yeah.
Is there some intuition there?
Yes, there is some intuition, but maybe.
Okay.
It's in that paper. We can have a look at.
Okay.
Together.
Yeah. And then the second question is sort of.
I mean, I was.
Right.
I was surprised.
It's surprising. Okay,
Yes,
so good.
yes.
Okay, that's good. But then, and then the second question, if it is, so if then in the first 2 orders, it's all captured by the geometry, basically, because it's a probe, then shouldn't it be, like, whether I put the black hole in n equals 8 or GR or whatever, it should always be the same
No,
results,
because
no?
n equal 8 has extra soft particle like the dilaton that couple.
Yes, but a
Right.
geodesic is a geodesic in the metric.
Yeah, exactly. So you can, so if you're calculating the probe trajectory in the appropriate n equal 8 geometry, then you find that 1 p.m. and 2 p.m. are derived. And actually, this was done in a very nice paper by Caron, Guo, and Zaré. Right? And there is this nice observation that the 2 p.m. result in n equal 8 in d equal 4 is 0.
Okay.
Right. Yeah.
Okay. Thanks.
You can maybe pass the microphone.
Since you mentioned the Moore, as far as I recall, at least some of your collaborators in he and also Twibern had a sort of, they didn't agree on the results, to put it mildly. So can you say what is the status of this debate?
Sorry, I didn't catch. What observable are you?
The more, at least Gabriele, I know, and Twibern, they calculated similar quantities.
Oh, yes. You refer to this 3 p.m. story.
And got different results.
Yeah, I'm coming to that. Yes.
Okay.
Yes, that's exact. These novelties.
So, but can you say?
Yes, and then if you are if you have more questions, of course, just ask. Yeah, so what? You see, at 3 p.m. there is much more interesting, right? So let me try to convey why it is more interesting, right? So, well, I think basically everything has to do to the fact that now there is a cut in the amplitude language, right? There is a 3-particle cut, so you can produce on-shell particle. Right, so think about this, the blue line and the red line are the classic massive objects, right? And then you have to insert all 3-level diagram in between, and you look at kind of this type H type of topology, and you can cut it along the dashed line. And cut means you put on shell each one of these particles. So the graviton, the black line, which is in the middle, that goes on shell, right? So the existence of this 3-particle cut tells us that the iconal, this delta, is not real anymore, becomes imaginary, right? So there is an imaginary part, and that imaginary part is actually captured by this cut. And this was already understood in the 90s by Amati, Ciafalone, and Veneziano. Now, related to this point, exactly the point that was raised, this shows that the 3PM result is not captured by potential graviton. So let me say, what does it mean, potential graviton? Potential graviton means that when you do your integration over your Feynman integration, right, over all the momenta of the particle exchanged, you focused on momenta, on gravitons that have the energy component almost zero, right? And the spatial component of the order 1 of h bar over b. And I call them potential because if you think about the Coulomb law, the potential of, this is exactly the type of soft particles, right? That have zero energy and then have q square on the spatial momentum, right? So what Bern and collaborator did is to focus on potential graviton to extract what is called the conservative part. That's something that I will not be discussing very much, but that's the standard approach that people use.
May I ask? Sorry. So this is a loop. It contains a loop of graviton because you talked about three levels.
Sorry, Igor. It does not contain a loop of graviton.
Because you are not a graviton. Okay.
This is not a graviton.
The second question is whether it cannot be reconstructed from a different geometry, that is a geometry which is Schwarzschild plus radiation.
Of course, I mean, that's exactly the game of this, I mean, conceptually at least, that's exactly the game of this effective one body, right? So what the problem you are asking is, what is the effective geometry of the effective one body theory that reproduces the scattering of this, right? It starts with Schwarzschild and then has correction. You want to understand those corrections, right?
So I agree that's the idea behind the construction of the effective one-body Hamiltonian, because you have the body system where you consider finite size from the mass ratio, but effective one-body needs the radiation reaction, so it's not just geometry, right? So yeah, it needs more information than just this. So
yeah,
it's the same effect. I agree.
This is one input, right? Then you use the balance equation.
Yes, exactly. But it's not just geometry. So you cannot find the form geometry produces this result.
Yes. Let me come more to this. Yes, I think. Exactly. I think that's all the same issue, right? So, okay. So let me try to answer this question, and let me do it for n equal 8 supergravity. GR works exactly the same. It's just the result will not stay on a slide, right? So n equal 8 supergravity stay in a slide, and also historically that's where we understood the problem. Right, and then after you understand n equals 8 supergravity, you can do it in GR. So you do exactly the same thing, right? You calculate now the full two-loop amplitude. You do the small q limit. The first term will be 1 over h bar cube, and that's no new information, right? And that's just a check that you're doing the right calculation. It should be the cube of the three-level diagram. The second term is also no new information. It should be the cross term between the three-level diagram and the one-loop diagram, right? So if you want to mine the new information, you have to go to the third subleading term. That's the new information. That gives you the subleading contribution to delta, right? The 3PM information, right? And it's this answer. And you see that first is not real, right? The first line is real, and then there is an I here. That's the imaginary part. So that imaginary part is because of that cut. Then in green, this result here, 1, that's the result that you would get by using just potential graviton. So if you want to extract a conservative part, ignoring radiation reaction, you find just that one. And that was a very nice paper by this group. Now, if you do the large sigma limit of just this result, it does not have a finite. It does not have it does not have a finite limit. It does not go over the massless result and does not have the form you expect. And that was the puzzle that you mentioned, right? Just stating the n equal 8, but GR has the same puzzle. So what we found is that if you find the full contribution, not just focusing on the potential graviton, but focusing on all gravitons, also those contributing to this cut, you find also this imaginary part and new terms in the real part, which are this one in blue. And these are the radiation reaction term. So these are terms due to the fact that the process, the elastic process does not exist, right? It always wants to radiate, right? And you see, the magic of these new terms is that A, they make the large sigma limit, the ultra-relativistic limit, well behaved. Because when sigma is large, this square parenthesis goes to 0. So this arc cosh, which is a log, drops, right? Because the coefficient goes to 0. And you are just left with this. That's the leading contribution to the high energy. And that leading contribution to the high energy is the universal bit, is the one that you will find in GR, in n equal 8, in n equal 4, right? And there were kind of a series of papers here understanding this bit by bit. And these terms in blue in the imaginary part are there because what we exploited is the analyticity structure of the amplitude. It links the radiation reaction terms to other terms. And so from the analyticity structure, you can deduce the radiation reaction term, right? So I'm just saying that, okay, from a particle physics point of view, you can have fun disentangling these various contributions. Okay, so this ends the what should have been the first part, and then in the last 5, I don't know, how much time do we have, 10 minutes? Yeah. In the last 10 minutes, I moved to a second part, but if there are any questions on this, please let me know. Yes, yes, so the agreement, the statement is that if you focus just on potential graviton, you get the result of Zwibern and collaborators, right? But that's not the physical iconal or physical deflection angle. So that's not the trajectory that the particle will really follow, right? That's an auxiliary problem that is relevant if you neglect radiation, right? If you just by hand say, okay, I just throw away all contributions that have to do with radiation. If you want to know the physical deflection angle, right, then you have the problem, you cannot ignore radiation, radiation exists, right? So you have this radiation reaction effect, and this radiation reaction effect do not change the structure of the answer that is already known. They add new terms, right? And they add these new terms in blue.
Yeah, I thought that the debate was about the existence of the log.
The existence of this?
The log in the...
Exactly, exactly. So what happens is that the log, which is this hyperbolic cosh, right, is there in the potential answer, right? But the radiation reaction term adds a contribution that cancels that, right? So you see that when sigma becomes very large, this becomes 1 minus 1.
So the original log that Gabriele and Paolo De Vecchia found, or Cifaloni, Veneziano found, is gone?
I'm not sure what log you are referring to.
There was a debate between Damour, Zwibern, and Gabriele Veneziano about that log.
Yeah,
that,
so the debate was the following, that you see it in this formula, in this first line. So in the Bern answer, you have a logarithmic enhancement at high energy. And what we, Gabriele, Paolo, and Carlo, were seeing is that that enhancement should not be there for the physical angle, right? And then the answer is that if you include radiation reaction term, so Damour, you have to ask, but I think you wanted to get rid of that log, right? You wanted to get rid of that log. So that's why I think in this paper of 2019, he tried to propose different ways to modify the answer of Bern to get rid of that log. But the outcome is exactly this radiation reaction, right? It's not something you guess, right? You can't calculate. And what is interesting from the post-Newtonian point of view, let me just say just this last sentence, which is related to this. If you do the opposite limit of this first line, you go to sigma goes to 1, small b, this potential part and this radiation reaction part have very different behavior. One has even power of the velocities and the other has odd power of the velocities, so 1 pn, 2 pn, and the other 2.5, 3.5. So you see the different nature of these two contributions from also the PN, the non-relativistic approximation. So I think 3 p.m. now is fully understood. And as I will probably mention in the conclusion, the game is for 4 p.m.
Actually, 5 is the real goal, right?
5 is the real goal, but you cannot score the second goal before scoring the first one, right? So you have to do 4 p.m. first. Very good. Okay, so let me be very brief, but just give an idea of something that we appeared today on the archive, and which is what we were focusing on in the last few months. And the idea is to, okay, is there a way to encode in a systematic way radiation, right? So far we discussed the scattering, right? And the virtual effect of the radiation, right? This radiation reaction effect. But in principle, we should also have a real radiation, right? That's what we measure is the gravitons, like the real radiation produced. So can one generalize this iconal approach to include real radiation? So the answer is yes, and there is work going on by several groups in this direction. And the idea is, let me just flash this formula here. You see that instead of talking about an iconal phase, which captures just the trajectory, you include new degrees of freedom, which are the real gravitons emitted. And these new degrees of freedom, I include them in a very naive way as a Fock space of gravitons. So I introduce creation and annihilation operators of gravitons of different momenta, right? So that K is the momentum of the real graviton. And I dress the iconal phase with a coherent type state of these real gravitons and produce not a phase, but now an iconal operator, right? An operator that produces many gravitons. And then you should ask, how do you calculate from amplitude these coefficients, right? So it's very similar approach, right? I told you how to calculate this delta, which encodes the information about the non-radiative part. And now how you calculate these coefficients. And these coefficients are related not to 4-point functions, but to these 5-point functions here, right? So look at this diagram, throw away half of it, and look at that. And those are the seeds of the new information that, that you need. From this iconal operator, you can calculate observables by taking expectation values of objects like, I don't know, the energy operator, the angular momentum operator, right, in the final state. So the idea is that you take this iconal operator, you act on a state with no gravitons, and that's the final state. Right? The final state will be the massive particle a bit deflected, plus a lot of gravitons produced by this exponential part. And then if you want to calculate an observable, the total energy radiated, or the spectrum, right? The energy radiated by in this cone, right? You put your observable here in this expectation value, and you just try to calculate. Notice that this iconal operator tells you that the elastic amplitude is heavily suppressed. When you put this and you have to normal order the operator, right? You have to use the Baker formula. Right? This normal ordering will produce for you this imaginary part, right? So you really see this imaginary part coming from the fact that there are new channels opening up, right? That there is this radiation. Yeah, this is one thing you can do. And then what we mainly focused on is this spectrum, the energy radiated. And there is a similar story to the problem of the high energy behavior that I discussed for the angle, also for this energy radiated. And you can ask, is it consistent, the result for the energy radiated? Yes. Yeah. Okay, Donato, can you unmute yourself and just speak up?
Yes, this was the answer to the question somebody raised when you were talking a few minutes ago.
I mean, this is Thibault speaking, yes. It was Ron Borstein, no, we was talking about this log. Maybe to clarify, Rodolfo is talking about n=8 supergravity. The first proof that
I think it's Thibault. Thibault, we can hear you.
The log is cancelled, okay, was given by me in this paper. In the chat.
Yeah, okay, I'm not sure I fully got everything, but I think what... Oh, wrote something in the chat, but I don't know how to read it. Maybe you can. No, I think one point no, because here is full screen. If I exit from full screen, maybe you can read it from there. No, what I think just what Bertrand was saying is that here I'm talking about n=8, but then the thing was, yes, exactly. Yeah, the first proof in GR is done in this paper here by Thibault. You see, this was, if you move this slightly, the window slightly. Sorry. Yeah, so this is in April, right? 2001, and there is a paper here in August 2008. So this is the first paper where we saw this radiation reaction effect in n=8. And then you see, immediately after, right, a month after, Thibault found a very nice proof of how to find this radiation reaction effect in GR with a different technique, not this amplitude based, but really a classical GR through a linear response formula that Donato and Thibault had, right? And so this story here that which here is kind of a bit easier, is generalized to GR, and you have the green terms, which are the one by Bern, much more complicated for GR, and the blue terms that are the radiation reaction. Then after that paper of Thibault, we repeated the amplitude analysis and reproduced Thibault analysis just from the amplitude. So it's nice to see how the story intertwines, right, from different approaches. And of course, correct me if I'm wrong, Donato, but I think now 3 p.m. is fully clarified, right? So we have that under control. Very good. So let me just mention that there is a similar problem in the high energy behavior now for the emitted energy. And we studied the version of this problem related to soft gravitons and clarified that aspect. But there is still open issue about the full spectrum. So what I want to say is that the scattering process has a more complicated spectrum than the bound process, right? The bound process has one main frequencies, right? Because it's a bound system, and then a discrete spectrum, right? Related to that frequency. The scattering problem has a continuous spectrum, right? So you have a dE over d omega for the different values of the frequency of the gravitons. When I say soft, I'm just looking at the very small omega region. And that part is what we studied in the paper that appeared today. But then you can ask about the whole spectrum, and that's still an open problem. So let me conclude. So I hope that I convey the idea that amplitude-based techniques are useful for studying the initial part. And even though I focused mainly on scattering, this information can be used also for the in-spiral. But for me, the main motivation is that the approach is flexible, can be applied to different theory, and gives a new conceptual view on the problem. And what kind of the motivation I was pursuing is try to give an answer to this question. Is it possible to model this classical object as elementary particle? And one nice test is to take this high energy limit and see whether there are problems coming up there. And you saw that the history was a bit involved, and apparently there were initially some problems, but then we understood how they are solved. And for the spinless case, all the situation is clarified within the traditional classical approach. So we didn't find any problem with point-like objects, spinless point-like objects up to 3 p.m. But is this, maybe to end with something kind of relevant for the workshop, is this the whole story? Is this always true, not just for Schwarzschild, but for Kerr, for even maybe more complicated object? My personal take is that I doubt that this is true, and my personal bet would be that Kerr is the most interesting interesting problem to study, because you have classical spin, and it's very hard to put classical spin with a point-like object. And from a string theorist point of view, you always think that when you have spin, object tends to become larger, right? So if you take a string and you try to put a lot of spin to that string, you have a classical, you have the string tends to become larger, right? So is that something that one is forced to do, or is this approach of point-like object always valid for the in-spiral part? Okay, thank you.
One question.
Okay, one simple question. Could you identify which is the Feynman diagram which is contributing to this 3 p.m., the new one, not the exponentiate?
The diagram that is contributing to the radiation reaction.
Exactly.
Okay, we don't talk about diagrams, right? So okay, what I'm writing here. So this is shaded, because you should not think about this as a diagram made out of 3-point vertices, right? That would be not a gauge invariant quantity, right? So what you do, you calculate the whole amplitude. So there will be this diagram with 4-point vertices, diagram where the 3 gravitons are all kind of going in this way. And you calculate the whole amplitude, and then you look at the cut at the whole amplitude, right? So what I'm saying is that the radiation reaction is captured by this cut.
My question is about the one with the 3 lines. I suppose that we contribute to exponentiate.
No, but it includes also to this, yeah. It
contributes also to this.
Yes. In order to have these blue factors, right? We did the whole calculation, right? Now there is a whole new development where people say, okay, we build confidence on the idea and we want to simplify. And there is my colleagues at Queen Mary, the group in Copenhagen, right? So they say, okay, we don't want to check the exponentiation. We want to get rid of those terms as early as possible in order to isolate the amplitude calculation that we can do at 4 p.m., right? So there is very interesting development also there to try to do it at earlier stage instead of doing the whole calculation and check at the end. But this is what we did, so I presented that the old way. So for this radiation reaction, yeah, okay, we can discuss, but if you just take the whole contribution and you throw it away, you don't get the right answer. So in order to take away the exponentiation, you have to be a bit smart, and that's what these new calculations are doing. They tell you what you have to throw away to just keep the part which is contributing to the classical term.
I was curious to know what is a typical time length that you can follow this inspiring phase, and when this breaks down, because I mean the two objects, I mean, starts merging together. Okay.
It is not a question for me. Maybe it's a question for the. No, from what I understand, yeah, from what I understand, the EOB approach goes quite far, right? I don't know, maybe last 3 orbits, 2, 4. Yeah. I mean, so it goes much more than I thought, right?
Anyway, you need these inputs then to essentially to inform also the merger part.
Exactly. I think that they match, but I'm not an expert of that. Yeah, sorry.
Another question. So following up on your last slide on the Kerr case, I was thinking about the spin, because so finite size effect, even before say the law of number, the title deformability, one can think about the multiple moments, right? The quadruple moment, and objects with the same spin can have a different quadruple moment. So I was wondering, in the Kerr case, I guess that you, instead of having scalar fields, you will have fields with spin, right? To model the amplitudes. But then how do you, I mean, how, is it the quadruple moment somehow of the objects, of the celestial objects incorporated, and how? Because I mean, the only information there will be the spin of the fields. So I can imagine you can model the spin, but how do you know whether it is a black hole or a neutron star?
Very good, very good. Yeah, I mean, I'm happy also to discuss separately, because this is kind of a developing story, and it's very, in some sense, the information about the geometry, the Kerr geometry, is entirely encoded in the 3-point function. So you have your heavy classical object now with a classical spin, and you say, what is the coupling with one graviton, right? Now, when you have spin, okay, there is also the spin, right? So it's not something you read from a Lagrangian, right? So there was a whole idea of guessing consistent couplings, right? And it's not unique, right? I mean, if I take a string states, right, with spin, and I have, depending on the level of the string states, I have different couplings, right?
So you have a free coefficient, and that probably
you have a lot of coefficients, right? Because it's you expand in A in the spin, right? And you have A squared. You have an infinite number of coefficients, right? So there is a nice paper by Arcani Ahmed, Huang, and collaborator, where they were just listing, just writing nice couplings, and there is in their formalism something that looked very nice, and they call it minimal coupling. But what Vines, Ochirov, and collaborator, I think they show, I'm not fully sure about the history, but I think what they show is that that coupling corresponds to Kerr, right? To the Kerr geometry, right? If you want to change the quadruple, you change those numbers, right? From an AFT point of view, you start changing the term with the A square with respect to A, or A to the 4th with respect to A square. But in some sense, this is not the most interesting part for me, because when you want to go on, you need also couplings with 2 gravitons, right? So things which is the top of this. Now, how do you read them, right? Now you don't have a Lagrangian and you can do the calculation, right? So defining those couplings of Kerr with 2 gravitons, it's what is the focus of these papers, recent papers here, right? So this is, I think, 10 days ago. And that's new information that is relevant for the inspiral, but is not related to the geometry. So in some sense, that's why I'm always a bit skeptical when people, I don't know, do love number or dynamics by looking just at the response for the geometry, because you are testing the geometry, you are not testing, you already put in the input that is the object is described by the geometry. There are objects, terms that are not related to the geometry, and these ones, and so,
I just wanted to follow up on that. So why isn't so these two gravitons coming out from the top, why isn't that just like two copies of the 3-point function that you're interested in? And this is not, it's because the middle state, you don't assume it's Kerr anymore, or? Well, you will emit them at the same point, but this
in some sense, it's a contact interaction, right?
Yeah, but do you care about these contact interactions for the? Okay.
In some sense, the part where you have just the 3-point coupling and twice, that's contribute to the exponentiation, right? Now, all the interesting story is the contribution subleading to that, and that's sensitive to what in a Lagrangian approach you would have contact term. And then you can take an EFT approach. That I think this paper here, this one, took that approach. You start writing Lagrangians, and then you say, I can do calculation, but then is it consistent? How do you fix the higher derivative term, right? Supplementary spin condition, high energy behavior. So there are lots of ways you try to constrain those terms.
But this is inherently beyond GR, anything that GR does then. Is that right or not?
Well, in some sense, no. They are asking what is Kerr? And what I'm saying is that saying that Kerr is the solution to the Einstein equation, that's one Kerr. But when you have two Kerrs, you don't know, right? So the question is, what is Kerr? Okay, looks to me a difficult question.
Are there more questions? Please.
Yeah, thanks. So there is something which I'm not sure if I don't understand it or I don't like it, which is you said that at 2 p.m., no, sorry, at 3 p.m. you have a radiation reaction, but then at the other order you have the computation of the waveforms or the gravitons emitted at infinity. If I understood. So you seem to make a distinction between radiation reaction, which is already in your computation. So your computation became imaginary, so it had a dissipative part at some order, but then you are computing the gravitational waves, in sense of the gravitons at the next order. But to me, these two things are the same thing, right? So radiation reaction is there because you are emitting gravitational waves, and so the system loses energy. So this should enter consistently. So as soon as you have radiation reaction, in a consistent framework, you should be able immediately to compute the gravitational waves. So am I missing something?
No, I think you are correct, and we fully agree. So you see this radiation reaction is G cube, and then it's just that I did the two calculations in two separate slides, but they are at the same order, right? So this is G cube, and then when you look at this energy radiated, you see there is a factor of Q square. Q is the deflection angle, and the deflection angle goes like G. So there is a G square hidden here, and there is a factor of G here. So it is exactly this 3 p.m. order, and I think this is why the 3 p.m. is interesting.
Okay, if there are no more questions, we thank again Rodolfo. And we resume 2:30.